My name is Manasi Sharma. I'm currently a senior in Columbia College studying computer science and physics. And last year, I graduated from the Lindenlaw Fellowship. And this year, I actually worked with Professor Anima Anandkumar at the Tensor Lab at Caltech on a project on causal inference. So to explain our research question, I'm going to give you a little bit of background first. In all the world around us, we can see data, observe it, and that's called observational data because we can measure it. There's also unobserved data that we actually can't measure directly, but which influences the data and variables around us. For example, in social media recommendation systems, we can measure how long a person looks at a specific video, for example, but we can't measure their internal preferences that cause them to pick that video. And so the idea behind causal inference is sort of modeling those relationships to help make better predictions in the future. And sort of my specific aim for the summer was to help optimize an algorithm that'd be able to sort of disentangle these causal effects from these sort of hidden variables and figure out exactly what those relationships are, how strong they are and in what direction they go. So to talk about my research methodologies a bit, I used a technique called intervention. So this is actually what happens when you have a variable influencing another and you fix the value of the first variable. And what happens is you sort of dislodge it from all the previous other variables that affect that variable, and you only study its effect on the secondary variable. And so by using that sort of interventional trick, we can generate an entire data set called interventional data. And there's a specific model that we use that combines in a new way the sort of interventional data with the observational data we can see around us to form what's called joint SEM-ICA model, or joint linear structural equation model, and independent component analysis. And the end goal of this is what we really want is two matrices that the algorithm will provide to us. One is called A and one is called B. Matrix A will show the relationship between the observed variables themselves, and the matrix B will show the relationship between the observed variables and the sort of hidden variables that I was talking about earlier, which we can't measure directly. With regards to my findings, I used a technique called competitive gradient descent to help optimize the algorithm. And to give you a slight idea of competitive gradient descent, essentially it's it's almost like a game where you have two players and they help make their next move by anticipating the player's other moves. In my case, the two players were two equations to minimize the two matrices I told you about earlier, A and B. And so by implementing a specific algorithm, I was able, by tuning hyperparameters in the model as well, through trial and error, I was able to reduce the mean squared error for the matrix B to around 0.01. And so my goal for the summer was successfully achieved, which was to successfully optimize the algorithm. And going forward, causal inference can be applied in a wide variety of fields, such as in medicine, disease diagnosis, where we can't know a person's preconditions, for example. And so I'm really excited to see all the applications of it in the future. Thank you for listening to me.